Good morning. And I would like to teach that is mathematics, statistics, operation research. It's a math and statistics. Both are having same operation research, and they're having both the topics are similar. And it is industry application oriented problems we will solve in this subject. Your operation research deals with some different kind of the application problems. In this operation research, for example, I'm taking that is some objective function is I want to maximize or I want to reduce that is a expenditure. I want to reduce the expenditure. That is the main objective. So at the time I will go for that is a minimization problem I will use. And when I want that is a maximize my profit, at the time I will use the maximize values. So here minimization or maximization, such kind of the problems are the maximum involved in this linear programming problem. In this operation research, it's the first is goes to the linear programming problem LPP. In this linear programming problem is design the problem by objective function. This is objective function is clearly defined the A1x1 plus A2x2 like that. Here A1, A2 so can take that is up to n variables and n constants also. Now, subjected to the constraints, if we take subjected to the constraints, that is called as a here we will put some conditions. The conditions target for that is a particular month. This is a capacity of the some 1,200 crores rupees target has to be complete. Unless it is 1,200 members has to be sell this product. Like here we are the keeping that is some product is being like that. Here something it is two industry areas. It is two products are available in that industry. The two products has to be that is X1 product and X2 product. The two products has to be sale in the market. The same within the areas wise, it is in Hyderabad, it is less than or equal to 200. This is Bombay, it is they want to be sale that is less than or equal to some 50. Like here, we can take that is a different kind of the constraints, but overall they want to be the expect that is a profit. How much profit is the maximum is a profit, including that is both the areas. Such a way we want to identify that is X1 and X2. Like here, wherever it is industry applications are involved, there we are applying that is a linear programming problem. In this linear programming problem, maximum all the problems are involved here, objective function, constraints, and restrictions. So in this, objective function is clearly defined maximization or minimization z equal to a1x1 plus a2x plus so on a3x plus so on nx. Now, subject to the constraints, if I take that, it is a something a11x1 plus a12 x2 less than or equal to some 200 or something. It is a value we can give that is it is called as a b1, and here a21 x1 plus a22 x2 is less than or equal to b2, and a31 x1 plus a32 x2 is less than or equal to b3. And similarly, we can take the number of constraints as per requirement. Sir, only less than or equal to, it is excessive sometimes, maybe expect that is expectations that is more than that also. So, some other constraints, if I take a41 x1 plus a42 x2, it is also greater than or equal to some b4. See here, less than or equal to or greater than or equal to. Now some constraints are having that is equal also. So it is a, if I take that is a A51x1 plus A52x2 is equal to B5. Now, in this continuation here, restrictions are x1, x2 greater than or equal to 0. So here, this kind of constraints, what are that constraints? It is a inequality or equality type of the constraints. Every industry is a maximum profit or minimum cost. So that such a way we are using that is a, what are the constraints they want to give, that company automatically will give. And based on that, here we have what the we'll consider that is a linear programming model. Such linear programming model we will solve by using that is our certain procedures. That procedures, first one is called as a graphical method. Second one is called as a simplex method. Today we will discuss about that is a graphical method. Here, generally it is a linear programming problem. It is contained that is objective function, either maximization or minimization set. It is a1x1 plus a2x2, subject to the constraints are the a1x1 plus a12x2 less than or equal to b1, and a21x1 plus a22x2 less than or equal to b2, a31x1 plus a32x2 less than or equal to b3, and so on. So here every constraint is involving the greater than or equal to or less than or equal to or equal to such type of the equalities or inequalities we consider as a constraints that are called as subject to the constraints. And the restrictions all are the, what are the unknown variables we have that is called as x1, x2 greater than or equal to 0. Here in this problem, we want to identify that is x1, x2s. How many x1, x2s we are getting, that all x1, x2s we will substitute in the objective function, which is a maximum or minimum, which is we want that it will get, that is called as optimal value or optimal solution we can identify. This is a overall idea about that is a linear programming problem. Here every industry is involved, that is a what is a motto that is called as objective function for them. And the restrictions and constraints, it is based on that, it is a total observations of that as the infrastructure and implementations, manpower, all the considerations. They will expect that is a such kind of the profit, so that all will be considered is the constraints and the restrictions. So these all are the constraints and restrictions. So we are identifying that is a objective on linear programming problem. We want to minimize or maximize the problem. In this today, I want to discuss that is a linear programming problem by the graphical method. I will take one example. From that, I will explain. Here, maximization z equal to some 2x1 plus 3x2 I am taking. Here, subject to the constraints STC. Here, x1 plus 2x2 is less than or equal to 4 and 2x1 plus x2 is greater than or equal to less than or equal to 6. Now x1 comma x2 is greater than or equal to 0. Now this example I'm taking here from the graphical method with the example problem solving of the problem. The first given problem we will take solution part given. In that constraints, the first step is a given problem we will take. Second step is a constraints are converting to the equalities. Constraints convert into equalities. In this conversion of the inequality, I will inequality into the equality. Here x1 plus 2x2 equal to 4 I will take. And find the points on the coordinate points of the where it is intersecting on the x-axis and x1 axis and x2 axis. That is, if I take x1 equal to 0, I will get that is x2 equal to 4 by 2 equal to 2. So point is we can get that is a 0 comma 2. This is the intersecting of the y-axis. It is on x2. Next, I'm taking that is x2 equal to 0. Then intersecting on x-axis, x1 axis, I'm considering here it is equal to the 4. So it is a 4. So that it is the point is 4 comma 0. Now, second, from this I will construct that is a graph. X1 axis and x2 axis. Because of I'm taking this is x1 is greater than or equal to 0, x2 also greater than or equal to. Both are the positive. We can get that this is a region only. So that is x1 axis and x2 axis. And from the first constraint equation, I'm going to construct here. It is a 0 comma 2. 0 comma 2 means it is a 0, 1, 2, 3. It is going for the 4. Now here 1, 2, 3, 4, 5. Now it is a x1 is the 0 and y x2 is the 2. So that I'm taking this point is this point. Next, so for x2 is a 0 and x1 equal to 4. So 4 comma 0. This is the point. Now joining up these 2 points, I will get that this is the equation is called as equation number 1. It is a equation number 1. Now I'm going to consider there is a second equation. It is a inequality is clearly less than or equal to. When we have a less than or equal to, move towards origin side. Region, move towards origin side. So it is a direction I'm taking to the origin side. You draw that is a graph, region. Next, another equation. Here 2x1 plus x2 less than or equal to 6. So here 2x1 plus x2 is less than or equal to 6. Make into the equality. So it is equal to 2 equal to 6. And x1 equal to 0. So x2 equal to 6. Where we get the point is a 0 comma 6. Here 0 comma 6 means it is a y-axis. The point will be extended up to. This is a 5 and this is a 6. This is a point. It's called as a 0 comma 6. Now coming to the x2 equal to 0. X2 equal to 0. What happens? X1 equal to 6 by 2. So we can get the 3. The respective point is a 3 comma 0. So I'm getting the point is a 3 comma 0. Joining these 2 points, this is a equation 2. Now it is also inequality is clearly less than or equal to constraint. Here less than or equal. Less than or equal to constraint, it means that already I mentioned it is a region you draw towards origin side. Origin means here this side. So here I'm drawing the region. What is the common region? That common region is called as a solution region. Both are intersecting the region. Both inequalities intersecting region is called as a solution region. This is called as a solution region. Here in this solution region, I'm giving the corner points OABC. These OABCs are called as a corner points of the solution. But OABC are called OABC corner points are called initial basic feasible solution. It is a all solutions. Better solutions are these corner solutions. That is called as a initial basic feasible solutions. Feasible solution region. Now, coming to the, I want to find out that is a optimal points. First, corner point is O is a 0, 0. Here, OABC, O, comma A, comma B, comma C are the corner points. These are called as initial basic feasible solutions. OABC is the feasible region, solution region. In that corner points is the initial basic feasible solutions are in that one of the solution is called as the best optimal solution. Now O is already know. A is the clearly we know that we found that is a 3 comma 0. Now B we don't know, that is we want to identify. It is the intersecting of the 2 lines that we will solve here, and C is clearly 0 comma 2. Now B calculation point of view, I will take that as a 2, equation 1 and equation 2. Equation 1 is x1 plus 2x2 equal to 4. And the 2x1 plus x2 equal to, second equation is clearly 6. Now solving of these two, here I will multiply first equation into the 2. This is the 4. This is 8. Subtracting both of the equations, this is a cancel. So here 3x2 equal to 2. So x equal to 2 by 3. Now we have that is a x1 plus 2x2 equal to 4. From the first equation, if I substitute that is x2, x1 plus 4 by 3 equal to 4. So here x1 equal to 4 minus 4 by 3. x1 equal to 12 minus 4, 8 by 3. So here x1 comma x2, we get that is a 8 by 3 comma 2 by 3. Now here I got it, the point is a 8 comma 2 by 3. This is a intersect region. This is a intersect by 8 comma 8 by 3 comma 2 by 3. Here we have that is a 0 comma 2. So these are the corner points called as in this objective function is maximization z equal to x1 plus 3x2. So here maximization z equal to 2x1 plus 3x2. Here first is a, I will substitute the point, it is a O. O if I substituted, I will get the solution 0 comma 0. So maximization z equal to here 2 into 0 plus 3 into 0, it is equal to the 0. Now A, I will substitute 3 comma 0. So here maximization z equal to here 2 into 3 plus here 0 into 0, so 6. Here B, here 8 by 3 comma 2 by 3, that equal to maximization z equal to here 2 into 8 by 3 plus 3 into 2 by 3. So here 16 by 3 plus 2. So 6, it means that 22 by 3. Next it comes to the here 3. Here I can get that is a simplification 6.72. So here I can go further. It is another point is a C. The C is goes to the points are 0 comma 2. So if I substitute 0 comma 2, I can get that is a maximization z equal to 2 times of 0 plus 3 times of 2, it is equal to 6. So here, out of which is a maximum? B point is gives that is a maximum. Therefore, maximization z equal to 6.7. Exactly, it is 22 by 3. And the maximum optimal solution is 8 by 3 comma 2 by 3. This is our required solution. Once again, listen what we did in this problem. Yeah, today I discussed about the operation research. In this, mainly it is a linear programming problem. It is a linear program problem represents that is an objective function. In this objective function, it is a maximization or minimization z equal to a1 x1 plus a2 x2. Subject to the constraints, it is a11 x1 plus a12 x2 is less than or equal to b1. It is a less than or equal to or greater than or equal to, whichever it will be there, equal to also it will be there. That is called as a constraint. And the restrictions are x1 comma x2 greater than or equal to 0. And the graphical method today we are discussing with the example. It is I'm taking the objective function and constraints and restrictions. From that, it is a constraints. First, you make it to the equalities and find out that is a from the intersecting points on the x1 axis and x2 axis. Such a way, I found that is the points at the 0, 2, 4, 0. That is its corresponding state line equation in the region of x1 and x2 plane. I'm drawing that is one state line equation that is called as equation number 1. We have seen here. Already inequality is x1 plus 2x2 is less than or equal to 4. So that here that is a region is drawing into the bottom side. It is less than or equal to. It is moving towards the origin side. This is a region. Another constraint here, it is a 2x1 plus x2 less than or equal to 6. That is converting into the equality. Here 2x1 plus x2 equal to 6. And we found that is a points at 0, 6, 3, 0. That 2, 3, 0, 6 and 3, 0, we are constructing that the state line equation is from the second equation that we can see here. It is also, it is less than or equal to, so it is the movements will be the region more movements towards the origin side. So it is whenever it is greater than or equal to movements towards the outside of the origin, means outside. But it is here less than or equal to, so that I'm taking to the region into the origin side. But is whichever the region is a common from the inequality 1 and inequality 2, such a way here which is the common region is called as that is a solution region. In this solution points, it is a best solution points are the corner points. So that it is a corner points. I'm finding it is corner points are called as initial basic feasible solutions. So that the initial basic feasible solutions we are taking here 0 is a 0, 0 origin and A is the 3, 0 because of already we found by using that is intersecting points on the x1 and x2. So here first point is a is intersecting on x-axis, x1 axis, so that it is a 3, 0. Intersecting on the y-axis is the C is a 0, 2. And both the lines are intersecting point is called as a B that I identified it is a 8 by 3, 2 by 3. So that is I got it that is a O, A, B, C points. This is corner points are called as a initial basic feasible solution. In this initial basic feasible solutions, we can get that is one of the solution, one of the in between these solutions, which is satisfied that is a maximization Z, which is a maximum value that is called as the optimal solution. So I'm solving here maximization Z equal to x1 plus 3x2. All the points I'm substituting here origin O 0, 0 and 3, 0 and 8 by 3, 2 by 3 and 0, 2. All if we substituted, which is a maximum, we got it at the point is B, it is a 22 by 3. So that this is a maximum, is maximization Z is called as a maximum optimal value is 22 by 3 and its optimal solution is 8 by 3, 2 by 3. This is a method for the solving of the graphical method, but this is applicable only for the 2 variables involved linear programming problems. If it is a more than 2 variables involved problems, so we can solve by using that is a simplex method. That concept we will discuss into the next class. This is a oral problem. Okay, thank you. Thank you all. We will wind up this session. We'll meet in the next class.